Today is Wednesday, October 12th, and this Friday we will have quiz 4. So it covers from 3.5 to 1.7. Okay? So Friday we have a quiz. And then, so please do your homework. And if you have questions, feel free to ask me. Okay? And so for those of you who haven't submitted your practice exam or exam correction and record, don't forget to do those, okay? You want to earn as many points as you are able to. Okay. So if you submit your practice exam but didn't get 10 points, probably because you forgot to estimate your total score or you missed some correction. Okay, so I give you this opportunity. You can resubmit. So write down the estimate total score and write down the correction using red pen and resubmit. Then you can get those points back. Okay, everybody? So if you don't get perfect scores on your practice exam or exam correction or record, you can resubmit to get perfect scores. All right. So last time we talked about exponential functions, right? We call b to the x, where b is the base. The base is a positive number. And it depends on the b. If the base is bigger than 1, then the exponential function is an increasing function, right? This is what it looks like. And it passes through the points 0, 1. Domain minus infinity to infinity, range 0, not included, to infinity. Right? And we have a y-intercept at 0, 1. Asymptote, we have a horizontal asymptote, y equals to 0. Do you remember that? And if the base b is between 0 and 1, then the exponential function is going to be a decreasing function. Look like that. Okay. And the domains do the same, all real numbers, range, they're positive numbers, and it's decreasing all the time. We have the same y-intercept 0, 1. And we also have the horizontal asymptote, y equals to 0. No vertical asymptotes. Do you remember that, everybody? Okay. And so last time, given a parent function. So remember those parent functions. And then you can do the transformations. Follow the order, and then you can write down the transformations in each step, and the formula in each step, the graph in each step. Okay, so let's continue. Base E. Okay, what is E? Have you seen the E before? Okay, yeah. So consider this expression: 1 plus 1 over x to the power of x. This function comes up in many disciplines, including finance, compound interest, population growth and decay, right? Chemistry, chemical decay, right? Half-life, those stuff. And the table on the right-hand side shows that what happened to this expression as x getting bigger, bigger, bigger. So this is a function of x, right? And you can see when we plug in x as 1, you get 1 plus 1 over 1 is 2, right? So 1 plus 1 is 2, raised to the power of 1. Therefore, we get 2. And then you can use your calculator. You plug in your x as 10. You get 2.59 something. And if you increase the x, okay, so x is bigger, bigger, bigger. Do you see this expression is converging to a number? And this number is E. So you know pi. Pi is 3.14 something, right? It's very useful because circle, area of a circle, pi r squared. circumference of a circle, 2 pi r, right? So pi is an important number. And today, another important number is e. Okay. So e is often referred to the natural exponential base. It turns out that e is an irrational number, just like pi or square root of 2. And we get e as approximately by 2.71828, etc. So it's a number slightly smaller than 3. Okay, but it's bigger than 1. So therefore, the graph, yeah, so e to the x has very many interesting properties. If you learn calculus, then we know that later. The derivative of exponential function e to the x is itself. This is quite special. Okay, so, and these are the practice problems. You can work on those as extra exercise at home. And application, compound interest. Okay, do you have bank accounts? Yeah, so how do we calculate? Well, this is a formula for interest compounded n times per year. Okay, so A equals P times 1 plus R over N raised to the power of N times T, where A is the balance in the accounts, right? It's current balance in the accounts. P is the principal. So P is the principal. Principal is the amount of money that you initially put into the accounts, right? Everybody? Principal. And R is the annual interest rate. So maybe 3%, 5%, 2%. Those are the annual interest rates. And then N is the number of compounding per year. So for example, if it says the account is compounded monthly, then N is 12 because 1 year has 12 months. Right, everybody? So N is the number of compoundings. And how about if we say compounded quarterly? How many quarters in a year? 4. That's why N equals 4. Okay. And T is the time in years. So 1 year or 2 years or 3 years, etc. And as N goes to infinity, the process approaches what is called continuously compounding. And we will get P, so this is parentheses 1 plus R over N to the power of NT. This will go to P times E to the RT. Why is that? Okay, let me share my audio. Can I share my audio? Okay. Something wrong with. Okay. Okay. I'm not able to share my audio, video. Okay. So, how to show that? Remember E? Okay. So 1 plus. So according to how do we get the E? 1 plus 1 over x. As x goes to infinity, this expression goes to E. Right, everybody? This is how we define the E. And then, now this guy, you can think of this, we write this as P times 1 plus R over N. Here, this NT, we divide it by R and multiply by R. Is that okay, everybody? Okay, I'm trying to show why this guy will convert to P times E to the RT. Okay, because now we rewrite this expression, the numerator, the exponent, we multiply by R and we divide it by R. Okay, now we let x be N over R. x be n over r. Then now you see r over n is the reciprocal of n over r. Therefore, this is 1 over x. Yes, everybody? Yes? Yes? So that's why r over n, that is 1 over x. And n over r, that is x. And then times rt. Okay, times rt is also the same as you have this guy raised to the power of rt. Now, as x goes to infinity, see, if n goes to infinity, then the x, see, the r is a constant because r is the annual interest rate. It's always fixed. Right, everybody? So r is constant. Therefore, if n is getting bigger, the x is getting bigger. Right? Therefore, this expression, 1 plus 1 over x raised to the power of x, this guy, it goes to y. Therefore, we have p times y. This expression goes to y and then raised to the power rt. So this is the proof, okay? This is our compound interest formula, and this is the proof when the n, the number of compoundings per year, goes to infinity, that expression will go to p times e to the rt. Okay, everybody? Yes. Awesome. Okay. Therefore, the exponential function, base b, very important. Because for quite few, many of our bank accounts, we compound continuously. So we're actually using this to calculate. Can I erase the board? Here? Okay. Oops. Let me. Here. Okay. All right. Okay. So, and because e is a number greater than 1, right? E is 2.7 something. So it's greater than 1. Then we know the picture will look like b to the x. Well, remember the base is greater than 1. Then we have an increasing function. Yes, everybody? We have an increasing function. So all this property we learned before remain the same. Yeah, everybody? Okay, so this is e to the rt. Oh, this is not the x-axis. This is now the t-axis. Okay, so change it to t-axis. And how about, so this is when r is positive. Okay, when r is positive, we have an increasing function like that. If r is negative, what happens? Well, if r is negative, you can think of this as like e to the negative 3 times raised to the power t. And this is like 1 over e cubed to the t. Now, do you see the base is 1 over e cubed? And this number is less than 1? Yeah? This number is less than 1. So remember, if the base is less than 1, we have a decreasing function. Therefore, if r, okay, look at the r. If r is positive, we have a increasing function. If r is negative, we have a decreasing function. Yes, everybody? Okay. All right. Let's continue. Okay. Let's do example 4. Example 4. Okay. So, by the way, today I lost my stylus pen, so I will use my finger. Then you expect my handwriting is not as good as before, but I will try my best. Okay. Okay. So let's write down the formula. Okay. So yeah, formula is very important. This is formula. A equals P times parentheses 1 plus annual interest rates R over N, okay, times raise the power of N T. Okay, so this is a formula. Okay, let's write it down. This formula. Oops, draw it. Okay. A equals P times 1 plus R, the annual interest rate, over N, raised to the power of NT. Okay, if the compounding continuously, we have the formula A equals P times E to the RT. So those are the two different formulas. Okay, first one. Quarterly, what is the N? 4, exactly. So we plug in, right? Invested $12,000. $12,000, that's the principal, right? And annual interest rate, 3%. Annual interest rate is R. Yes, everybody? R is 3%. By the way, what's 3%? 0.03. Yes, very good. Find the balance after 5 years. So 5 years, that's the time, right? Okay, now we have all the information. Plug into the formula. So A equals P is 12,000. And then 1 plus R, which is 0.03. Over N. What's N? 4. Raised to the power of N, which is 4, times T. What's T? 5. Okay, plug this in your calculator. What do you get? Give me 2 decimal places. Yeah, everybody learn how to use your calculator. Okay, 12,000 parentheses. 1 plus 0.3 over 4 raised to the power. 4 times 5. Please bring your calculator to class from now on, okay? Alright. So what do you get? I got 13,934.21. Point what? 2-1. Oh, thank you. Do you have the same answer, everybody? If yes, that's good. If not, check your work. What did you type in your calculator? Awesome. Okay. Part B. Monthly. What's your N? Monthly, what's your N? 12. Oh, you see, part B is very similar to part A, but you replace N by 12. Exactly. So we have P is the same, 12,000. 1 plus R is still 0.03. Now N is 12. Bless you. And then N is 12 times T is 5. Okay, so if you have your calculator, you can go up to the previous line and replace 4 by 12. Okay, so you don't need to type the whole thing again. You can go up to the line and then you can delete the 4 and then click insert the 12. What number do you get? 900 and what? 39. Point what? 40. Thank you. Yes. Oh, do you see this number is bigger than that number? Yeah, and it makes sense because the more compounding you do, the more money you get. Right. Okay, part C. Continuously. Well, continuously, then we use the formula, oh, how do I, okay. Me? Okay, continuously, we use the formula P times e to the RT. P is 12,000 and times e to the okay, what happened? It's kind of slow here. Okay, yes, e to the RT. R is 0.03. T is 5, right? So you type that in your calculator. What do you get? Do you see a calculator? Can you see the E? Yeah? So you type 12,000 and then times, press that E button. E raised to the power 0.03 times 5. What do you get?
13,942.01.
Thank you. So 13,942.01. Yeah, everybody? Questions? Do you get different answers? Let's see. Very short. Hey? Do you have a knee? Where is it? Oh, yeah, there. You need to buy another calculator. Yeah, so TI-34, you're TI-30. So E, oh, it's right here. Oh, you don't have E, you don't have LN. So, yeah, yes. Okay, so you need to buy another calculator. Yeah, so make sure your calculator has the E and LN. By the way, no graphing calculator. Make sure you have a scientific calculator with the E. Yes. Okay. Yes, everybody? All right. So this is the example. So we just use the formula and then we can plug in the numbers. And by the way, no formula sheets will be provided for precalculus class. So please try your best to memorize those formulas. Okay? Principal, 1 plus your annual interest rate. But because you're compounding like more than 1 times per year, that's why each time you compound it is R over N. Okay, so your annual interest rate is let's say 0.5. Okay, then if you compound it 4 times, then each time your interest rate is gonna be the annual interest rate divided by 4. Right? Can you imagine everybody? Because the R is the annual, it's the whole year, but you compound it 4 times. So that's why the interest rate for each time you divide it by 4. Okay? And raise to the power of 4 because you're compounding 4 times. Every time you compound it, you multiply a copy of it. That's why the 4 is right here. And one more year, you have another copy. That's why the 5 the time is also on the exponent. Okay, so this is the formula. And then any questions about this worksheet? Okay, so this is 4.1 and 4.2. We talk about exponential function and the graphs, and we have an example, real life applications for it. Okay, and then let's see. Next one, 4.3. Okay, so 4.3, logarithm functions and their graphs. So motivation. How do we solve the following equations for x? Okay, So if we have 5x equals 3, how do we solve for x? What operation we do on both sides? Divided by 5, exactly, right? So x equals 3 over 5, okay? Because multiplication and division, they are inverse operations. That's why we want to get rid of the 5, we divided both sides by 5. And here, how do we solve for x? Square both sides, right, everybody? That is because square roots and square, they are reverse operation. So we square both sides. We get 2 squared equals 4. Okay, how about the next one? This is what? Cube roots. How do you get x? 3. Both sides raise to the power of 3, right? So, yeah. Both sides raised to the power of 3. So both sides raised to the power of 3. Now do you see, because exponent rule, x to the a to the power of b is x to the a times b. That's why 1/3 raised to the power of 3, you actually multiply by 1/3 and 3 together. So you get 1. Yes, everybody? So that's why, oh, x equals, what is 4 cubed? 64, yes. Okay, next one. 2 to the x equals to 7. How do we find the x? Well, last time, if we have 2 to the x equals 2 to the 5, what is x? 5, right? If we make sure that on your both hand sides the base are the same, then we just set the exponents to be equal, right? This is last time, we know that. But now, our right hand side, we have 7. 7 is not base 2. Therefore, we need to undo the exponential function. In other words, we want to find the inverse of the exponential function. And that is the logarithmic function. Okay? So to solve x will be logarithmic function. And the base is 2, 7. So this is the answer. But let's look at our definition of the log function. Oops, sorry. Okay, yes. So we want to undo the exponential function. So we want to find the inverse of the exponential function. Is this function invertible? Why? Okay, so this is the exponential function b to the x where the, okay. So this is the exponential function b to the x where b is greater than 1. We know it is an increasing function. It passed through the point 0, 1, and here it has a horizontal asymptote y equal to 0. Do you remember that from last time? Okay, so how do we find the inverse function? Well, in order to find the inverse function, this function must be 1 to 1. Okay, so if the function invertible, is the same as asking is the function f 1 to 1. Look at the graph of f. Is this function 1 to 1? Remember, to test whether a graph is a function, you use vertical line test. To test whether a graph is a 1 to 1 function, you use horizontal line test. So you intersect the graph with all the horizontal lines. Do you see it intersects only like at most once for all the horizontal lines? Do you see that? For all the horizontal lines, it only intersects at most once. Do you see that, everybody? So this function is 1-to-1. Okay, yes, it's 1-to-1, and we use the horizontal line test. Okay, horizontal line test. Sorry, today my stylus pen, I lost my stylus pen, so my handwriting is not pretty today. Okay. All right. So yeah, it's 1-to-1. So inverse functions exist. And how do we find an inverse function? We call that the inverse function, and the function are mirror image about the line y equals x. So y equals x is this line, yeah? This is y equals x. Yeah? Okay. Something wrong with my... Okay, yes. Y equals x is the line. So mirror image. What mirror image means? Well, you pick some points on this graph. Okay, let's say this point. Mirror image means you draw a line that's perpendicular to this line, right? Okay, this is like a mirror. You draw a line perpendicular to it, and then on this line you travel the same distance. Therefore, the mirror image of the point 0, 1 is going to be 1, 0. Yes, everybody? Oops. Okay, I want to draw it. So 1, 0 right here. And how about let's pick more points? Let's pick this point. So you draw a line perpendicular to it, and then you travel the same distance to find the mirror image. Yes, everybody? Okay, let's pick another point. One more point, let's say here. Okay, so you draw a line perpendicular to it, and then you travel the same distance. So this is the mirror image. Yes, everybody? So therefore, oh, we have 1, 2, 3, 3 points. We connect them smoothly. So we connect them smoothly. This is the graph of the inverse function. Okay, everybody? All right. Okay, so y equals b to the x is the exponential function. And here, now the inverse function, we have so x will be log b of y. Okay? So this is the inputs. Oops. Inputs. And that's the output. Okay? Now, when you try to solve for x, you want to have, x is the input, now it becomes the output. And then this inverse function, you have y is become the input, right? So, yeah, oops. Okay. This is just very easy to touch it, okay? So, yeah, so we have function y equals f of x. Then when you apply the inverse function, you get f inverse y equals x. Okay, now this guy becomes the output, and the y becomes the input. That's the inverse function. Okay, and now let's see definition of the logarithmic function. Let me shrink this a little bit. Okay, wait, what happened? Okay. Hey, what is this? Okay. Let's see here. How do I? Okay, with this one. Oh, this one. Okay, I pressed the wrong button. Okay, the logarithm functions. Since the power space b is greater than 0 and not equal to 1, if f of x equals b to the x, we define the inverse function to be log b of x. The base is b. Okay, the logarithmic base b of x. The property is, so we have the logarithm form and the exponential form. A equals b to the c. B is the base. So, and then c is equal to log base b of a. Okay? So it's like you interchange the inputs and outputs. Okay? So, for example, let's look at some example. Okay, let's look at some example. So, okay, so 3 square is 9. Okay, then if this is the exponential form, the logarithmic form will be 2, okay, equals log 3, the base is 3, okay, and 9. So you kind of put the input to the output. So the exponents 2 is going to be log 3. Base stays still the same. Okay, so this little number, okay, the subscript of the log function, that is the base of 9. So 9 was the output, now it becomes the input. So that is the exponential form and logarithm form. And because they are inverse function, so you know that log b of b to the x equals x. That's the property of inverse function. You apply f and then you apply f inverse, you just get the same thing. Okay, so therefore log b of b to the x is just x. Okay, and also b to the log b of x, this is also x. Remember the property of the inverse function? Yeah, f composite f inverse, you get the x back. And f inverse composite with f, you also get the x back. That's the property of inverse function. Therefore, because exponential function and the logarithm function, they are inverse functions. So therefore, if you apply the exponential function first and then the logarithm function, they will kind of cancel. You just get your x back. Or you apply the logarithm function first and then the exponential function, they will also cancel. You just get x back. Is that okay, everybody? We are using the properties of inverse functions. Okay, very good. Now keep going. Common log. Okay, so log, if you don't see the base, we assume the base is 10. Okay? If the base is e, then we use the notation natural log ln. Okay? Natural log ln to denote. Okay, so ln, that means base is e. Or if you don't see any base, we assume the base is 10. So that's why on your calculator, do you see the button log and ln? So that's the log function, base e and base 10. That's it, log. Right. Okay, let's do some problems. Example 1. Evaluate the following log functions. Okay, so let's, yeah. Okay, go down. Okay, let's do it. We know the property that log b to the x is x. And we know b to the log bx is also equal to x. So we want to transform this so that they express the a's in a way so that they have the same base. What's 8? What's 8? 2 to the, what's 8? 2 to the 3. Yes, everybody. Now, let's see. Log base 2 and the exponential function base 2. They cancel, right, everybody? So log 2 to cancel. What's left? 3, exactly. So as long as you express those so that this is the same, then they can cancel. You just get x back. Okay. How about here? What's your base? What's your base? 8. Can you transform 64 as a squared? Exactly. So this is log 8 squared. So what's that? 2. Yes. Right, everybody? Okay, how about this one? Okay, can you transform the 1 to base 6? 6 to the what is 1? Yes. Oops. Sorry. This is yeah, I touched the button very easily. Okay. Right, everybody? 1 is 6 to the 0. Oh, what's that? 0, exactly. Yeah. Okay. And now we keep going. Okay? So that is one way how to solve this type of problem. Okay? There is another way to solve this type of problems. And remember, if you have like b to the x equals to y, then x equals log b of y. So keep that in mind. They are inverse functions. So b to the x equals to y. That means x equals log b of y. Do you agree, everybody? Mm-hmm. So now set this equals to x. Okay, set this equal to x. And see, log by equals x. So now you want to write down the exponential form. What's the b? 1/2. So this means 1/2. Okay, what is the exponent? X. See, b to the x. The x equals what? Equals 4. Is everybody okay with that? So we have the logarithm form and change to exponential form. Sometimes if you forget, write it down. E to the x equals to y. So then x equals log b of y. Okay? Your b is the base. So here the base is 1/2. It stays in the base. But now your output becomes the input. Your input becomes the output. Okay? Now, okay. So let's transform both sides with the same base. What's 1/2? 2 to the -1. Exactly. So on the left hand side, we have 2 to the -1. So something wrong with my pen. Okay, 2. Okay, right here. 2 to the -1 to the x is 2 to the -x. Is that okay, everybody? Mm-hmm. On your right hand side, what is 4? 2 squared. Oh, do you see both of them have the same base? Now you just set the exponent to be the same, right? So according to the facts we learned last time, if they have the same base, you just set the exponent be the same. So minus x equals 2. See? And minus x equals to 2. Then what is x? -2. Yeah, very good. Okay. So can you do part E and F? Let's see. This side of the room do part E first and then F. And you guys do part F first and then E. Okay. So do it. Using that method. Write down the exponential form. You write both sides so you have the same things. Okay, let's check our work. So what do you have? You set equals to x, right? What do you get? 27 power x equals 1/3. What's 27? 3 cubed. Yeah? Raised to the power of x is, what's 1/3? Yeah. And remember, we have the property of exponent rule. 3 to the cube and raised to the power of x. We can multiply the exponents. Right, everybody? So that's why we get 3x equals -1. So x equals -1/3. Is that okay, everybody? All right. Next one. We set this equals to x. And then what happened? Oops. Okay. What's the base? 7 to the x equals cube root of 49. What is 49? 7 squared. Exactly. Hey. Hi. Cube root of 49. Hey, I write a 4, but it doesn't let me to write a 4. What happened? Okay, this is just driving me crazy. Okay, so 49 is 7 squared, right? And the cube root is like to the 1/3, right, everybody? So this is the same as 2/3. Okay, now you make sure both sides have the same base. What's your x? Yeah, 2/3. So far, so good, everybody? Yeah, I would say if your base is very simple, use this method. Yeah, here, you can also use this method. But if your base is not simple, like 1/2 or 27, then use the second method. Okay, everybody? Which method do you prefer? The top one, if the base is easy, the top one method is easier, right? But if your base get harder, then use the second method. Is that clear, everybody? All right. Okay, let's continue. Okay, so let's recall the graph of uh, exponential function, and then we want to draw the graph of the logarithmic function. So I want to shrink it. Okay, so I want to shrink it a little bit so you can see them. Okay, so we already draw the inverse function, right? The inverse functions is, oh, how about let me pull out the notes with answer to save some time. Okay, yeah. Is that okay? I pull out the notes with answers because it's hard to draw like this. Okay, so this is the exponential function. And how we draw the inverse function, we draw the line y equals x, and then we figure out the mirror image. You plus some points, and then you draw the line perpendicular to this mirror, and you travel the same distance. So that's the mirror image. And then here, this point, the mirror image is here. This point, the mirror image is here. And then you connect all those 3 points together. You get, this is the graph of the log d of x. So far, so good, everybody? So this is when b is greater than 1. Now, what properties do we have? Now, because inverse function, do you see the domain and range flip interchange? Yeah. So our domain is now the range. See your range from minus infinity to positive infinity. And our range is become the domain. See your domain from 0 open to positive infinity. Do you see that, everybody? And it's increasing all the time, right? So both the exponential function and the logarithmic function, if the b is bigger than 1, we get increasing functions. And here, oh, we don't have y-intercept, but we have the x-intercept. So the x-intercept is 1, 0. Okay, everybody? And we have a vertical asymptote. See? Vertical asymptote is x equal to 0. And we do not have horizontal asymptote. Right, everybody? You see, the exponential function, we have horizontal asymptote. But when we flip it over here, it becomes the vertical asymptote. So for the logarithmic function, we have the vertical asymptote, x equal to 0. And we do not have horizontal asymptote. Now this is the new parent function. Okay, exponential function like this. The logarithmic function like that. Okay, so like that. Okay. So keep that in mind. Now, do you remember when we compute domains? We have the square root of a, then we need the a to be greater or equal to 0. If we have fractions, we require the denominator not equal to 0. Now add one more, logarithmic function. So ln of a, logarithmic function. We need the things inside the log to be positive. Okay, so add one more function to our list. Yes, everybody? Okay. Yeah, remember ln is base e, log base 10. So actually this is true for all the logs. So you can put log log b of a. Okay. Then we require the a to be greater than 0. Awesome. How about when b is a number between 0 and 1? Okay. If b is a number between 0 and 1, we know that exponential function is a decreasing function. It goes like that. Do you remember that, everybody? Then when we draw the inverse function, we draw the line y equals x. And we also put some key points. Look at this key point. This point, we flip it over, we get this point. And let's look at this point. We flip it over. You see it becomes here. Yeah. You draw the line perpendicular to the mirror, and you travel the same distance. You get this point. Yes, everybody? And one more point here. So the mirror image is kind of here. And then we connect these 3 points together. We get the graph of the logarithm function where the base is between 0 and 1. And we can see from the picture, domain, all real numbers. See, it goes to infinity, and here it goes to minus infinity. The domain, y values, all real numbers. Oops, sorry, that was the range. That's the range. The y values, all real numbers. The x values project down on the x-axis. Then you can see we have 0, not including the 0, and then to infinity. The domain is from 0 to infinity, range all real numbers. And you can see it's always decreasing. And we have no y-intercept, but we have an x-intercept, 1, 0. Do we have vertical asymptote? Do we have vertical asymptote? Mm-hmm. The line, while x equals to 0. Yeah, vertical line, x equals to a number. Do we have horizontal asymptote? No. Yes, everybody? Mm-hmm. Awesome. Okay, now example 2. Let's do example 2. Okay, let's do example 2. Find the domain of each functions. Okay, so I want to make it bigger. Find the domain of each functions. Write your answers using interval notation. Okay, so yeah, now our list, we have 3 functions: square roots, fractions, and log. Do you see this problem, part A? Do we have square roots? No. Do we have fractions? No. But we have log. Okay, so we need the things inside the log. So 9 minus x squared. The things inside the log to be greater than 0. Is that okay, everybody? Mm-hmm. And how do we solve inequality? First of all, my habits, I love to work with positive leading coefficients. So what I would do is I would multiply both sides by -1 so that I have a positive leading coefficients. Okay, but you don't have to follow this way. Just remember, if your leading coefficient is positive, you start with the right top corner. If your leading coefficient is negative, you start with the right lower corner. Yes, everybody? Okay. So there are many ways to solve inequality. So just my personal habit, I love to multiply both sides by -1. Then I have x squared minus 9. What happened to the inequality sign? Flips. So we have x squared minus 9 is less than 0. Is that okay, everybody? Mm-hmm. And then, by the way, some students put x squared, move the 9 to the other side and then take square root. So we have x less than plus or minus 3. We cannot do that. You move to the other side and then take square roots. This method only works for equation. Okay? For inequality, we cannot do that. So what we should do is we need to, let me make it smaller. Okay, what we need to do is we need to factor it. Okay. Okay, so we factor it. Okay, so here we cannot do that. Be careful. We want to factor it. How do you factor x squared minus 9? Yeah, very good. And what's the critical number? -3 and +3, right? Critical number is you set each factor equals 0. And you solve for x. That's why x plus 3 equals to 0. We subtract 3 on both sides. We get x equals to minus 3. And on the other hand, we add 3 on both sides. We get x equals to 3. So those are the critical number, -3 and 3. Okay, now, open circle or solid circle? Open, because it's less than, right? Okay, leading coefficient is 1, right? Leading coefficient is 1, which is positive. So we start with the right upper corner, right? And 3. 3 corresponds to the factor x minus 3. What's the multiplicity? What's the multiplicity? 1. Yeah, the exponent of the power of the factor is 1. 1 is add. So we cross, right? How about here? Cross again. So this is plus, this is plus, this is minus. And we are looking for what? Positive or negative? Negative, right? See, negative. Therefore, it's from -3 to +3. Open. So that is the domain of part A. Questions? No, not original. This one. Yes. So after we get the leading coefficient is positive, then we look at here.
On your notes on my note as -1.
Oh yes. So let me see what was on my notes. Yes. So on my notes, I do the same thing, but this is a critical number. But because now I didn't flip it, I didn't multiply both sides by -1. My leading coefficient is negative, so that's why I start with the right lower corner. And you see, we're looking for positive, so you have the same answer. Okay, so you don't have to make the leading coefficient positive. You can do both ways. Just make sure you don't get confused. Okay. Yes. Any questions? Have a nice day. So Friday, do we have a quiz on Friday? Yeah. So don't forget we have a quiz on Friday. Bye.